Hi, this is an example problem from Chapter 18. Deals with relating electric force and electric field. Pause for a moment and read the question. So if we look at this problem, we see that there's a picture here, and we got a charge in the center. I call this a source charge because it's the charge that creates, its presence creates the electric field everywhere out in space. Everywhere in space there's an electric field. We've drawn a few here that are on a circle around the charge. Since this is a point charge, we know that the equation for the electric field due to a source charge that's a point charge, it looks like this. It's based on Coulomb's law. And it almost looks like Coulomb's law, except we only have one charge, right? And so that charge Q is generating that field out in space. We don't care about it in this problem. We don't need to use that because we were already told that anywhere at any of those points, we've got this value of the electric field 20 newtons per coulomb. And we know that it's the same anywhere because if you look at R to any of these points, it's the same radius, right? So R is the same here. So is the electric field. Now, given that E everywhere is equal to 20 newtons per coulomb, we can use that to calculate what force is going to be exerted if we put other charges at those points in space. Let's look at A here. Determine the electric force exerted on a charge Q0, in this case, is equal to minus 5 coulombs. What are we going to use to figure this out? Well, there's a simple relationship between force and electric field. So the force on a charge, say I take this charge Q0, and I'm going to place it at 0.1 here. All right, here's Q0. It's equal to negative 5 coulombs. I've placed it there. How is it going to be affected? Well, we know it's going to be pushed straight up away from the source charge, right? The relationship between field and force says the force of that push upwards, I take the charge and I multiply it by the electric field at that point in space. If I only want to know the magnitude, I can go ahead and take the absolute value of both sides of this equation, and if I want, rewrite it like this. The magnitude of the force is just equal to the magnitude of the charge times the magnitude of the field. Now, there's a little hint here. It says use unit analysis to do this conversion between electric field and electric force. Well, let's go ahead and use that equation. We'll see that's exactly what it is. So for part A, the force exerted on that charge Q0 up at 0.1, that's going to be equal to the magnitude of Q0 multiplied by the electric field at that point. We know the magnitude of Q0 is 5 coulombs. And the electric field there, it's equal to 20 newtons per coulomb. That means for each coulomb of charge placed at that point, you get a force of 20 newtons. Here we've put 5 coulombs, so we're going to get a force of 100 newtons here. That's the magnitude. Cancel our coulombs out, we can see. And that's our force. Now to get the direction, we've been asked to do it counterclockwise from the positive x-axis, right? So if we think about that, think of directions, right? If this is the positive x-axis here, plus x, this is what we call 0 degrees. Straight up plus y, we call 90 degrees. Over here to the left, we call this 180 degrees. And this direction straight down is 270 degrees. Now if I draw the force vector that's acting on charge 1 at Q0 at 0.1, we know that the source charge is going to attract it, right? It's a negative charge, so it's going to point straight down. That's your force there for part A. And notice that if we think of this vector equation here, get rid of the absolute values for a second, and just think of this as a vector equation, we can see that the electric field and the force, these guys are proportional, but the charge, the sign here, can flip the sign of the vector, right? So if Q is positive, F and E point in the same direction, but if Q0 is negative, F is opposite. In other words, anytime you put a negative charge in the electric field, the force is going to point opposite the field as you see it there. All right, let's do part B. For part B, we're going to go ahead and look at a charge plus 2.5 newtons, sorry, plus 2.5 coulombs, and we're going to put it at 0.3. So here it is. And so that's a Q0. I'm ignoring the green charge, pretend it's not there anymore, but the source charge is still there. We put 2.5 newtons here, positive. Sorry, coulombs, keep saying that. Positive charge. And what am I going to get for the force? Well, let's go ahead and calculate it. In this case, I put a different Q0 at a different point. The charge in this case is 2.5 coulombs. The electric field at that point is the same magnitude, 20 newtons per coulomb. And that means I'm going to get 20 newtons per each coulomb, 2.5 coulombs. Cancel those coulombs out. We're going to end up with 50 newtons of force on that charge, right? Coulombs canceled out. And now we just got to draw the force vector, right? In this case, it's a positive charge. The source charge is going to push it away. But a simpler way to think about that is, well, this is a positive charge we place in the field. It's going to point in the same direction as the electric field. Positive charges just do that. All right, let's look at part C here. Finally, for part C, we're going to take a 10 coulomb charge. We're going to put it at 0.6. Let's use blue for this one. So right here, now I'm going to ignore the green and the purple. Those charges are gone. We've removed them. The source charge is still there, though. And we've just put this test charge here. Test charge is just another word for a different charge, not the source charge. And this one's equal to plus 10 coulombs. Same thing as before. We're going to go ahead and do this calculation for the electric field. Now in this case, the charge we've used is 10 coulombs, and we've placed it a region in space where the electric field is 20 newtons per coulomb. So for each of those 10 coulombs, we're getting 20 newtons. That means we get 200 newtons of force there. And there's your magnitude. Now, I've forgotten to put the directions in part A and B. So for part A, we can see this was part A. This was part B over here. And so for part A, if it points straight down, that's in the direction 270 degrees. Counterclockwise from positive x. For part B, we can see it points straight towards the x-axis. That's going to be 0 degrees. Counterclockwise from plus x-axis. And now if we look at for part C here, we've got a point charge there at 0.6. It's positive. We know it's going to be repelled from the source charge, but simpler, we can go ahead and just say it's a positive charge. The force will be in the same direction as the electric field at that point. So I can go ahead and just draw it like this. And I'm going to draw it longer because it's a longer force vector, right? And if I look at that, well, turns out that it's a nice perfect little angle here, right? 180, how much additional do we need to go counterclockwise? 45 degrees, right? So the angle there, we can just look at it from the geometry. It comes out to 225 degrees. And again, same specification. We end up with this here. And so those are all the answers that we have for this particular problem. Again, look that it's pretty straightforward if you know the electric field to calculate the force on a charge placed at that particular location in space.